Okay, this is 3-7, and I am looking at the homework set that is assigned after having done examples 5 and 6. Number 1 and 2, I don't think you'll have a problem setting those up. You have some very similar examples in your notes, but 3 and 5 are kind of interesting questions. So I wanted to kind of help you get that set up so you can have success on your homework here. And we've got this owner of an orange grove estimates that if 24 trees are planted per acre, then each mature tree will yield 600 oranges per year. So we've got 24 trees, that's per acre. We can expect a yield of 600 oranges per tree each year. And for each additional tree planted per acre, the number of oranges produced by each tree decreases by 12. How many trees should be planted per acre to obtain the most oranges per year? So there's some sweet spot here where I should go ahead and increase my trees, even though it's going to reduce the overall yield a little bit. So where's that sweet spot? So let's let X equal the number of trees in excess of 24 per acre. Then I know that the yield, see, that would give me 24 plus X. That'd be trees per acre, wouldn't it? And the yield that is associated with that number of trees is going to be 600 oranges per tree minus 12 times X, 12 times the number of trees that we have exceeded the 24, and that'll be oranges per tree. So each tree is going to drop by 12 times the number of trees in excess of 24. So I think what I've been scratching out here, 600 oranges per tree minus 12x oranges per tree, we can simplify that as 600 minus 12x being the yield or oranges per tree. Now, we want to we want to obtain the most, which tells me we want to maximize the situation. So what would our equation look like? This is all helper stuff that we've been writing down so far. Now let's write an equation that talks about the yield, really the total yield, isn't it? The total yield. So the total yield is going to be really the number of trees multiplied by the number of oranges per tree. Kind of a simple thought here for a moment. And then we'll see our trees canceling, won't we? And we'll end up with an answer in oranges. So this is good. So our total yield, let's go, f of x is going to equal the number of trees, 24 plus x, times the yield, which is 600 minus 12x. And that should give us amount of oranges. So there's the setup. I think from this point forward, you should be able to take it over, and really you're just taking the derivative, looking for the max value. Number 4, posters being designed to contain 150 square inches of printed material with margins of 2 inches at the top, bottom, and 3 inches on the side. What overall dimensions will maximize the amount of paper used? For that, why don't you first just draw yourself a picture of the scenario. So you've got this poster, and then you're going to have margins on that, and the margins are going to be a little different, 2 inches at the top and bottom and 3 inches at the side, so a little bit more on the sides than what we have on top and bottom. So design that it contains 150 square inches, and we know that this would be X, wouldn't we? And then Y. Let's see, the printed material is going to be X, and the printed material may be Y there. And then you've got, you're picking up 3 inches on each side, and you're picking up 2 inches above and below. So you can tack that onto your overall dimensions and then how much paper will be used. The poster is being designed to contain 150 inches of printed material with margins of 2 and 3 inches. What overall dimensions will minimize the amount of paper used? So I think I would just go ahead and know that area is really just length times width, and our length times our width, and we know our length of our paper is going to be y plus 6, and we know the width of our paper is going to be x plus 6. That should have been a 4 with our y, shouldn't it? That was 2 inches on top and bottom. And then I think you can substitute that in. Another fact you know is that you want the area x times y, the inside area, the printed area, to be 150 square inches. So this, I think, is going to be perhaps your helper equation. And then you want overall dimensions. The overall dimensions will minimize. So bring in that length of y plus 4 and that width of x plus 6. Do a little substituting with your helper equation here, and I think you're going to be able to take the derivative you want to minimize on this. So take a derivative. There's a little setup on 4. I guess I stopped and got sidetracked. 5, find the dimensions of the rectangle with the maximum area inscribed in a semicircle with radius of 8 inches. Okay, so we have a semicircle, and oops, that didn't work so well for me. I'll try to redo. So semicircle and cut off there. And then we've got a rectangle with a maximum area inscribed in a semicircle. Okay, so we want a rectangle sitting inside here, don't we? Something like that. We know where the center of our circle is, or semicircle, let's call it there. And it told us this was a distance of 8 inches. The radius of the semicircle was 8 inches. And since our rectangle is inscribed, that tells us these points have to coincide there. They have to intersect. Now you want to find the radius. I maybe would set up x, and a y here, and find the dimensions of the rectangle with a maximum area. So you want to maximize your rectangle. So the area of the rectangle could be described as 2x's, that's its length, times its height of y. And then, of course, that gives us 2 variables. So what's the helper equation? I think that's where we can make use of our 8-inch radius semicircle. So if we had to describe the equation of this circle, we would have x squared plus y squared equals 8 squared, the radius squared. And we're just going to center this thing at 0, 0. And that equation should work quite nicely. And since we want to, maybe you want to solve for y, so let's go y squared is equal to 64 minus x squared. We want the positive y, so I'm just going to take the positive square root on this. And now I've got something that I can substitute over in. So this ended up being our helper equation here. It has that constraint of the radius being 8 built into it. It's going to flow into this area problem over here where we can do some nice substitutions of bringing in 64 minus x squared, and then we want to square root that. I'll go a half on that. But looks like it's going to be maybe a product rule coming your way. So have fun with that one. That got you set up on that. Number 6 is a size of a bacteria population. Food grows. Determine when the bacteria will reach its maximum size. Well, this is a growth equation that they're giving us, and we just really want to maximize that. So this is actually pretty straightforward. Just go P prime of T and find its maximum point. Not a whole lot of work involved on that. Just use quotient rule. And then 7 is much like example number 6 that we did for notes. And I'll let you try to figure out 8. Excellent. Have a good day.